Hello, this is Mr. White, and this video is intended to quickly provide a few examples for applying the S equals R theta formula. And I'll first start by reminding you that using this formula requires that you be working with radian measures. So theta must be measured in radian if you are to use this formula. If by chance you are doing a problem that gives you a measurement in degrees or working in degrees, well, you need to first convert to radians, otherwise you may not use this formula. Alright, here are the three examples I'm going to be doing in this video. I'm not going to have any exercises for you to try on your own. Pause if you need to, take a look at these three examples, and you may decide that you don't need to see one or two of them. Feel free to fast forward ahead, of course, to the second and third one if you like. I'm going to go ahead and move the second and third one out of the way here and get started on the first one. Alright, first, we are given a sector here. Sector is just sort of a fancy geometry vocabulary term for a pie slice, if you like. And this sector has a central angle of 1.8 radian, and it has a perimeter of 25 meters. And given that information, we are to find out what the radius is. First thing I want to point out is that, like many textbooks or tests you may take, this figure is definitely not to scale. And I hope you recognize that. As you get more comfortable with what the radian measure is and what it means, that should become pretty apparent to you. Remember that that radian measure of an angle is defined to be the ratio of arc length divided by radius. And when we look at that figure, we see that the arc length to radius measures they look to be about the same length. So for this figure, we would say that theta looks to be about 1, because the arc length and radius have a roughly 1-to-1 ratio. You can tell that 1.8 ratio is not reasonable, but we're going to work with this figure anyway. I just wanted to point out, really emphasize that being aware of the definition of radian measure at all times would be beneficial to you. Let's go ahead. We are told that theta in this not-to-scale picture is 1.8 radian. We don't know what either the radius or the arc length is. That's not given to us directly. So let's go ahead and define those as variables. And one of the main things that I see students do that bothers me is that they'll assign variables like x and y. I guess that's not totally unreasonable, but we've already got variables for arc length and radius, so don't use x and y. Use r and theta and s. R for radius, and the convention is s for arc length. And since all radii of a circle are equal, we'll also call that one r. Please don't give that a separate variable. Those are both those radii have length r. So we can certainly write an equation. Given this piece of information that the perimeter is 25 meters, we can certainly say this radius plus this other radius plus this arc length equals 25 meters. And if you're recalling from algebra that when you have two variables, you need two independent equations to solve the equation, or system of equations. We need another equation. In other words, this single equation is not enough information alone to solve for these two variables. So what is our other equation? Well, it's S equals R theta. And recalling that in this case, theta is 1.8 radian. And since it is a radian measure, I use the formula. S equals R times 1.8. Now with those two equations together, we can solve for these variables. So let's go back to the first equation and rewrite it as 2r. I just added these two r's. Plus s. But instead of s, I'm going to substitute in what s equals. In terms of r, 1.8 r equals 25 meters. Add them all up. I think it's pretty clear from here. I hope to you. 3.8 r equals 25 meters. Using a little bit of mental math, I can approximate that and say, well, that's about 4r. 4r equals 25. I'd say r is probably going to be somewhere around 6, right? But I'll go ahead and grab the calculator and compute that r is about equal to 6.579 meters. rounded to 3 decimal places. I have answered the question, but if I want to go ahead and calculate the arc length, I'd say the arc length, of course, is 1.8 times that radius that I just calculated. And again, using the calculator, I'll get that S is approximately equal to 11.842 meters. Practicing a little quick mental math just to see if that makes sense. I say that if the radius is about 6.5 meters, then 2 radii together would be about 13 meters. 13 added to this arc length, which is about 12-ish. 13 plus 12-ish does give us 25 meters, so it all seems to make sense, right? All right, let's go on to the second example. All right, here a circular ring is cut into 3 equal pieces. The outer arc-shaped edge is 14 inches, the inner arc-shaped edge is 11 inches. How wide is the ring? We're not provided a picture this time, so we'll go ahead and have to draw it. And we'll make certain assumptions here. When we say a ring, we're assuming that we're dealing with a shape that's basically 2 circles, concentric circles. They have the same center points. And let's see, it's cut into 3 equal pieces. The only way that this could really be cut into 3 equal pieces is to perhaps slice it, let's see, like this, and I'll try to, do the best I can, cut that into about 3 equal pieces. And we are told that the outer arc-shaped edge is 14 inches. So, talking about that edge right there. And once again, let's use the conventions for assigning these variables. Let's call that S equals 14 inches. And then we're told that the inside edge, the inner arc-shaped edge, is 11 inches. So once again, we want to call that S equals 11 inches, but we're realizing that we can't really call both of those edges S. I do want to use that convention of S for arc length, so let's call the first one S1. Let's call the second one S2. I don't really care which one you call S1 and S2 as long as you're consistent and keep them straight, which is the outer, which is the inner. So we're calling S1 the outer in this case. And let's see, we're asked how wide is the ring? Well, first glance it may seem like we don't have enough information, but we actually do. Notice that since this ring is cut into 3 equal shapes, we can figure out what theta is. Now, my drawing's getting a little bit messy here, and in fact, I feel like I'll go ahead and just erase some of the clutter. I really only need to focus on one piece, right? And I'll notice that both of those arcs, the outer and the inner arc, both have the same central angle. So if I draw that angle there, I notice that that angle is equal to 1/3 of a circle. Now please don't think 120 degrees. Instead think that the whole circle is 2 pi radian, and we just took that entire 2 pi radian and cut it into 3 equal pieces. Therefore, this angle is 2 pi over 3 radian. I did, maybe a little bigger. Magic of the smartboard, right? All right. I've labeled just about everything I think I could, except for we need to kind of refocus on what is it we're supposed to find here. We're supposed to find how wide is the ring. In other words, how wide is this track? And it's constant width, so it doesn't really matter where along that track I look. But let's go ahead and look down here, and I could give that another variable if I like. I could call that W, and that would not be unreasonable for W for width. But let's do something else. We can anticipate that the formula we're going to use is S equals R theta, right? We can tell that's coming up real soon. We haven't labeled the radii at all here. So let's go ahead and label the radii. I would generally advise these types of problems to go ahead and label all your relevant angles, arcs, and radii, and then see if you really need to define any more variables. Quite often the answer is no. Let's call this R1 to go along with S1. And let's likewise call that inner radius, let's call that R2 to go along with S2. And notice that while I could define that track width right here as W or whatever if I like, I can also just say, I got enough letters here. My job is to find the width R2 minus R1. I hope you look at the picture. Oh, wait a minute. It's caught an error there. The way I define this, the width is R1 minus R2, right? That's the width I'm looking for. So let's proceed to find what R1 minus R2 is. We know that we'll be using S equals R theta. But let's point out that S equals R theta can be rearranged to get R by itself. That's the same as saying R equals S over theta. And in this case, I'm going to start by looking for R1 equals S1 over theta, which in this case is, let's see, 14 inches divided by 2 pi over 3. I could go ahead and simplify at this point, and I don't blame you if you do, but I've got enough experience where I'm going to say I'm going to hold off, and we'll see why I hold off here in just a moment. This up here, I'm going to real quickly do a similar equation for the inner radius. See, R2, of course, is going to be S2 divided by theta, which equals 11 inches over 2 pi over 3. And the reason I decided to hold off is it's not a big deal, but I can save a little bit of time. I can save a little bit of time by then saying that the width that I'm looking for, R1 minus R2, is going to be 14 inches over 2 pi over 3 minus 11 inches over 2 pi over 3. And I see that I have a common denominator. Again, I repeat, not a big deal if we had simplified earlier. It's really just from experience that I decided to hold off a bit. And the last thing I need to do is just simplify that. Knowing all of the fractions, I know that 3 inches divided by 2 pi over 3 is the same as 3 inches times the reciprocal, 3 over 2 pi. That's going to give us 9 over 2 pi inches. I could leave it like that, but if I feel compelled to go ahead and type it into my calculator, I'd get about 1.432 inches. And that is the track width. Pause on that one if you need to, look it over. Again, the general strategy is to really focus on S, R, and theta, and avoid using any extra variables if you are able. All right, let's go on to the last example. All right, the width of the figure in the track shown is 3 feet. This time, last time we're asked to essentially find the width of that ring or that track, if you want to look at it that way. This time we're given the width. It's given to be 3 feet wide, and the red edge is 20 feet. I did realize recently that I had a student who's colorblind, so apologies for that. This is the red edge here. And the blue edge is what we already tended to find, the length of that entire blue edge. This is an interesting problem because at first glance it seems to give very little information, and we are going to make an assumption or two here. But it seems to give too little information to find what we're looking for. But if we really focus on what we need to find and what we do know and can figure out, we'll be okay. So let's start with the assumptions. We are going to assume that, and quite often in the textbook or test they'll be more explicitly stated, but we are going to assume that these arcs, both the red and the blue one, sweep out angles of 90 degrees or pi over 2 radian. And we will assume that once you get past the arcs, that we have some straightaway sections that are just straight line segments. Now notice we are not given the length of those line segments. So let's again get to work just labeling what it is we know and we need to find out. Let's go ahead and call this S1, and let's call this outer one S2. You know, I think in the last example, I think I did S1 as the outer one and S2 as the inner, but it doesn't really matter, again, as long as you're consistent. So what I mean by that is, again, I'll say that this radius here, I'm being consistent by now labeling that one R1. And the outer one, the outer radius, as R2. At least I'm being consistent. Now, I do have some straightaway sections that seem to be relevant, so let's go ahead and label those. actually, before we get to the straightaway, let's go ahead and just state for the record that the angle we're dealing with here. My drawing's getting a little bit cluttered here, but I'll say that angle is definitely 90 degrees, but rather than write 90 degrees, I'm going to say theta equals the entire 2 pi radians of that circle divided into 4 equal pieces. I hope that makes sense. The entire 2 pi radians of an entire circle divided by 4. Or, of course, I could simplify that, reduce it down to pi over 2. All right, as for the straightaways, I'm not given any information at all on those. So I will go ahead and label those as variables, and S and R and theta don't apply to those variables, so I'll just label them whatever I want. Notice that that straightaway there is the same length as that straightaway, so I do not need 2 separate variables. I'll call them both A. Similarly, these 2 straightaways are the same length. I don't know anything about them, so I'll call them B. Okay, I've labeled just about as much as I can, and now I need to focus on what is it I'm supposed to find? I'm supposed to find the length of that blue edge. So the blue edge looks to be this length of B plus this length A over here plus S2. And of course, using our S equals R theta formula, I could also write that as B plus A plus R2, oops, B plus A plus, I need to write, R2 times theta. Now we know what theta is, right? We know theta is pi over 2, so let's go ahead and plug that in. And this looks ugly and intimidating, but I promise you it'll clean up to find this problem is not nearly as bad as we think it is. That's what we're supposed to find. Let's now consider something that, let's look at the other edge. Let's notice that the red edge equals, same deal, B plus A, this straightaway plus this straightaway, plus S1, which is B plus A plus R1 times pi over 2, the same value theta. And I'm giving some information on that one. I'm told that that one equals 20 feet. That was given information. So I'll go ahead and set that equals 20 feet. Now, I don't blame you if you're still looking at this thinking, I don't really know what I'm going to do with this. But here's the little trick. We know this. We know this red equation, and we want to know the blue expression. And you notice that they have some similar form there. We see that this looks very similar to this. That should provide us a little bit of hope. And there is one more piece of information that I realized I didn't really put on the picture. We're told that the width of the track is 3 feet. We're told that this distance right here is 3 feet. So let's go ahead and write this equation that R2, the length of the blue radius, is equal to R1 plus 3 feet. And when I observe that, I admit that it's kind of hard for a student who's new to this to kind of get the sense of all of this, but that's why I'm showing it to you. Let's substitute that in to our original equation, or to our blue expression. That means that the blue track is B plus A plus R1 plus 3 feet times pi over 2. Let me clear a little more space for myself here. We're getting close to the end. Let's go ahead and distribute out that pi over 2. That's B plus A plus R1 pi over 2 plus 3 pi over 2 feet. And I hope it's evident. I just distributed that pi over 2 through the terms inside the parentheses. And now we see a breakthrough here. Look at what we have here. All this mess is equal to 20 feet. We can substitute in 20 feet for all of this. Oops, got a little bit too anxious there. All of this. Notice in the red equation below that that's what equals 20 feet. So we have a bit of an aha moment. We go, apparently my blue expression is equal to 20 feet plus 3 pi over 2 feet. I'll send the page a little one more time. If I feel compelled to type that in the calculator, I'll find that 20 plus 3 pi over 2 gives about 24.712 feet if I go to 3 decimal places. That's the width or the length of the blue track. Notice that we were able to determine that without ever finding out what x and y and R1 and R2 were. Turns out there was not enough information to find those individually, yet we were able to find out this total length of the blue track. Turns out that does not depend on those terms, on those quantities individually. All right, so if you're wondering as a student, how are you supposed to see all this? It's not necessarily going to come smoothly. You may have to play around with it and wrestle with it for a bit. But that's part of the experience. So I hope this example is helpful.